In this lesson, we're going to study how the routing in the Internet is organized and scaled. Then we will discuss one of the linked state routing protocols, OSPF, which is the acronym for Open Shortest Path First. So far, we have studied a theoretical and simple world where all routers are the same, and the Internet is one giant flat network. However, this idealized Internet does not exist. First, this flat network does not scale. Routers can't possibly store all the Internet destinations in routing tables. There are just too many destinations, and the exchange of gigantic routing tables would cause a massive denial of service. Second, for functional and political reasons, countries, ISPs, and other organizations want to control routing in their own domains. Scalable routing is achieved by aggregating the routers into administrative domains known as autonomous systems. There are two types of routing within ASes. Within an AS domain, which is called Intra-AS Routing, and secondly, Inter-AS Routing, which is routing among the different autonomous systems. For Intra-AS Routing, all routing within the same AS must use the same routing protocol. But other AS administrators can choose a different Intra-AS routing protocol for their own domains. To communicate with other autonomous systems, a gateway router must be set up at the edge of its own autonomous system. This gateway router, which is called an AS boundary router, will be running the protocols for both Intra-AS and Inter-AS routing. The forwarding table of each gateway router contains both internal autonomous system routes and external routes to the AS. The internal routes are computed by Intra-AS routing, and the routes to external destinations are computed by both Intra-AS and Inter-AS routing. In this diagram, we see the interconnected autonomous systems, AS1 and AS2 and AS3, as well as connections to other networks. Where should a router in AS1 send a packet that it receives if that packet must be sent outside of its autonomous system? There are two possible paths out, through AS2 or AS3. Inter-AS routing determines the correct path and must propagate this information to all of the routers in AS1. There are several Intra-AS routing protocols that are also known as interior gateway protocols. The earliest protocol was RIP, a distance vector protocol. RIP packets run under UDP. OSPF and ISIS are linked state IGP routing protocols. We will discuss these in a little more detail in the ensuing slides. There's another protocol developed by Cisco. It's a proprietary Intra-AS protocol called Interior Gateway Routing Protocol. This also uses a distance vector algorithm. As stated before, OSPF is a linked state routing protocol using Dijkstra's algorithm to compute the routes. The O in OSPF stands for open because the protocol is publicly available, as opposed to a proprietary one. With OSPF, every router maintains a linked state database, which is essentially the network topology map. OSPF uses flooding to exchange the linked state advertisements between routers. Any change in routing information is flooded to all the routers in the entire autonomous system. After initialization, OSPF sends updates only in the routing table sections which have changed, thus avoiding sending the entire routing table. OSPF operates at the network layer. OSPF messages are encapsulated in IP packets as an IP payload. Now, because of this, there are two versions of OSPF, one for IP version 4 and one for IP version 6. IS is very similar to OSPF and is commonly used in large ISP network backbones. One difference is that IS operates at the data link layer. Thus, the switch from IP version 4 to IP version 6 requires no change in the protocol. The OSPF protocol supports authentication to prevent unwanted routing updates from being received and processed by the routers. If authentication is configured on a router, it will authenticate the source of each OSPF packet by using a password, which is known by both routers. As we discussed in the chapter introduction video, the best path in link state is determined by the path with the lowest cumulative cost. The cost of a link in OSPF is inversely proportional to the bandwidth of that link. That is, a higher bandwidth indicates a lower cost. This cost is also called a metric. In the past, OSPF allowed the use of the TOS bits to set cost metrics, but that is not typically used anymore. If there are multiple routes to a network with the same route type and cost, OSPF can install these routes in the routing table, and the router will load balance across these multiple paths. A router interface with OSPF usually advertises link costs to neighboring routers through multicast. Now, for large domains, an OSPF network can be divided into areas that are logical groupings of hosts and networks. This division is hierarchical. The backbone area, called Area 0, is the area that connects to the outside world via a boundary router. The boundary router connects the autonomous system to the outside internet. All other areas connect to Area 0 via area border routers. Each area maintains a separate link state database of its local routes. Each area border router summarizes these routes for use by the rest of the autonomous system by advertising this information to the other area border routers. Thus, the topology of an area is unknown outside the area. This reduces the routing traffic between parts of an autonomous system. The backbone routers run OSPF for routing within the backbone. The boundary router advertises the AS to the internet and redistributes the external routes into the AS. In the next video, we will discuss the routing protocol BGP, the glue that holds the internet together.